It's 3 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good to hear. All right, it's Wednesday, week 4. All right, so today, first thing we're going to do today is we're going to finish up the lecture on dimensional analysis from yesterday. So we kind of left off in the middle of an example. So I want to finish that up, and then we're also going to talk about some common dimensionless groups for fluid mechanics as well. And then from there, we're going to jump into what I would consider kind of the final, I would say major topic we're covering in this class, which is pipe flow. So my plan is to start that today, and then we'll finish it up the rest of it after the midterm tomorrow. And then that will be kind of the last major thing you'll need for homework 4. Okay. Speaking of kind of the schedule for the class, the next couple Thursdays will be very eventful. So tomorrow, obviously, we have our midterm 2. So that's going to be tomorrow in the first half of the class. So midterm 2 is going to start at 3 o'clock tomorrow. It's going to go until 4:20. So please make sure you guys are here on time to take the exam. In terms of content for midterm 2, remember there is a study guide that's posted. The main problems that you can expect are all covered in homework 3. So the solutions for homework 3 are also on Canvas as well. So please make sure you check those out as you're studying and preparing for the midterm tomorrow. Okay. In terms of what you can please bring your writing utensil, please bring a calculator, and just like the first midterm exam, you can bring one 8.5 by 11 sheet of notes. Okay. All right, and so that's everything for tomorrow, and then final exam will be next week. So we talked about it a little bit yesterday, but just to kind of reemphasize it again, next week we are going to cover new material, just because there is still stuff that we need to learn in fluids. But everything next week, I'm going to put less emphasis on the problems that we're doing and kind of more emphasis on just the conceptual stuff. So you can expect the stuff we cover next week to be on the final exam, but only in conceptual forms. And so you can expect only just like a short answer question or 2 based on what we cover next week. Okay. And then just like the midterm exams, you can expect a study guide for the final exam to come out early next week. It is going to be a comprehensive exam, cumulative, that's the word I was looking for. But it's not going to be absolutely everything in the class. And so I will cover stuff kind of from the first midterm, some stuff from the second midterm, but I am going to cut some content out just because, otherwise it would just be way too much to study, especially with, the shortened summer session. And so in terms of, overall content for the class that you can expect on the final exam, you can expect probably about half the stuff that we've covered in total in the summer session will be responsible for. Okay. So what I'm thinking right now is probably one topic from the first midterm, one topic for the second midterm, and then everything we've covered since the second midterm, which is potential flow, dimensional analysis, pipe flow, and the stuff we're going to cover next. Okay. But we'll talk about it, I think, more in detail early next week because I think right now I think you guys can do it. In terms of homework, remember homework 4 is due this weekend. I'm not planning on assigning another homework just because I want you guys to focus on studying for the final exam after this midterm. So homework 4 will be the last one. And then after that, just preparing for the final exam from okay. All right. Any questions I can answer before we get started for today? Yes.
When do you think of the study guide out?
Probably Monday. Yeah.
Can we get it earlier?
Sure. Yeah, I can probably put it together Friday. How about that? Okay. Yeah, I'll put the study guide together by Friday.
Is the final going to be the same time length as the midterms, or is it going to be longer?
It's going to be the whole session. So you have the full 3 hours for the final. I'm not going to write a 3-hour exam, though. I'm going to write the exam as if it was going to be a regular semester, which is a 2-hour exam. So basically, the format for the final I'm thinking of is 6 short answer questions and 4 problems. So just maybe about like a third longer than our midterm. Okay. Any other questions before we begin? Okay, all right, so let's go ahead and pick up where we left off. My dad called me right before the lecture and I told him I'm teaching right now. He said, "Oh, I butt dialed you on accident." He just messaged me. Okay, all right, so let's just kind of review the examples that we were covering last time. Okay. So remember, the whole point of the lecture yesterday was dimensional analysis, which kind of is, like I mentioned yesterday, kind of a strange topic to include in a fluid mechanics class. It's really kind of more of an experimental topic in experimental design. But it obviously does have applications in fluids. Okay. And so the example that we talked about last time, the example we kind of left off on was, basically an illustration of how we can use the information from yesterday to actually design an experiment. Okay. And so the example we're looking at is basically the drag force on a freeway sign, or I guess technically it's a freeway billboard. That's kind of what we said with how big it was. Right. So we have this kind of very huge, very large rectangular surface here. Right. It has a width. The width here was 35 feet. It has a height of 20 feet. Right. So what we said, this is obviously way too large to test in practice. And so there's no, there are wind tunnels that are this big, but typically you don't want to use them for something like this. Okay. We have atmospheric winds that are blowing at the surface of the sign, just like this. Okay. And because of the formation of the wake, we have some drag force that's going to be impacted onto the billboard that goes in that direction. Okay. And what we said was that we wanted to design an experiment so that we can measure this drag force or estimate it without having to do a full scale test. Okay. And what we said was that the wind coming in has a certain velocity, it has a certain density, and a certain viscosity. Okay. All right, and then through dimensional analysis, we obtained the following three-dimensional proofs. Was we said that the drag force, when you scale it in proportion to the density, you scale in proportion to the width squared, velocity squared is equal to a function of the ratio of the width divided by the height and the Reynolds number, which was mu divided by rho times v times w. Okay. Okay. So those are the three non-dimensional numbers that we said were relevant for this particular situation. And what we saw last time was that, we basically said that our testing chamber or our testing apparatus for this experiment had a maximum height constraint of 5 feet. And so we scaled the rest of the parameters in the experiment to fit that, smaller scale experiment. Okay. So this is a very common, you're going to come across this very commonly in practice, right? You have to scale down an experiment to just fit whatever the resources that you have, right? And so what we saw was that, first thing, we were saying if the height is limited to 5 feet, then in order to maintain kind of the same geometric similarity, we have to scale down the width as well, right? And so the width must be scaled down to 8.75 feet. Okay. Right. And because what we said was that, even though we're running a smaller scale experiment, one of our non-dimensional numbers here, okay, one of our non-dimensional numbers is the aspect ratio, basically just the ratio of the width divided by the height. And so what we said was that in our experiment, our aspect ratio should be the same as our full scale simulation or full scale situation. Okay. And so in order to maintain the same aspect ratio with a maximum height of 5 feet, then we have to scale the width down to 8.75 feet. Okay. All right, and then what we also said was that we're also going to scale our air velocity. Okay. So in the full scale, situation, what we said was that the air velocity can vary between 10 miles per hour and 60 miles per hour. which is, the average expected winds that you can expect that this billboard is going to be exposed to. Okay. But for our experiment, we actually need to speed this up. And so what we found is that our experiment actually had to scale up the velocity by a factor of 4. Right, so the experiment needs velocities of 40 miles per hour to 240 miles per hour. And the reason for that is that we needed to maintain the same value of our Reynolds number, which is our second non-dimensional number. Right, and so for reducing W, we're reducing the width by a factor of 4. That means in order to maintain the same Reynolds number, this non-dimensional number here, we essentially multiply our velocity by 4, but keep that consistent. Okay. All right, so that's kind of where we ended last time. Basically, learning how to take a situation like this and scale it according to the non-dimensional numbers. Okay. The last thing I wanted to mention about this example here was how we typically view the results. Okay. So let's say that you've made this determination, you've run your experiment, and you're ready to kind of present your results or display your results in some kind of scientific report. Okay. Now, what's unique is that we can use these same non-dimensional numbers to present the results. Okay. Because what the hope is that we're going to run this experiment and it's not going to be a trivial exercise. It's going to take, it takes a lot of work, it takes a lot of effort to set up a test like this. And so typically, you don't want to be running too many of these if you can use someone else's data. Okay. So the hope is that by running this experiment and getting this data, we can use these results to basically state what we think would happen for any rectangular sign. Okay. So the hope is that we're going to run this experiment. We're doing it in a way to keep these non-dimensional numbers consistent, and we can then take these results to say, what if we have a slightly bigger sign? What if we have a slightly smaller sign, right? Instead of running a whole different set of tests for a different sign, we can take these results and generalize to them. Okay, and the way we do that is we basically use our non-dimensional numbers here to plot the results. So you'll see this very often. And so if you read any scientific paper involving a fluids experiment, then you'll see the results presented in the following. Okay. And so for instance, you'll see a graph, something like this. Okay. Right. And you want to plot the relationship between one non-dimensional number compared to the other. Okay. And so in our case here, our dependent variable was our drag force. Okay. But instead of having the drag force being plotted on the vertical axis, we can instead plot the non-dimensional number associated with the drag force instead. Okay. So on the vertical axis here, we can have FD, but we're going to have this non-dimensional form. So we have FD divided by rho times the width squared times the velocity squared. Okay. And then on the horizontal axis, we can have another non-dimensional number, which in our case will be the Reynolds number. Okay. We can also test the aspect ratio. That's also interesting as well. But for this particular experiment, we're not varying the aspect ratio. We are varying the velocity. Okay. All right. And so in fact, I'm gonna actually invert the Reynolds number So velocity is on top, so we have rho times the velocity times the width divided by the viscosity. Okay. So don't be intimidated. I think the first time I think people see plots like this, figures like this in a paper, it looks like there's just a lot of, you just have like an alphabet soup of variables that are kind of flying all over the place. There's a reason that, you know, the results are displayed in this way, just so that the results can be generalizable to other situations. Okay. And let's say that, you know, generally as you know, and this kind of goes beyond this topic here, but generally as you increase the velocity, as you increase the Reynolds number, the drag force goes. So you'll have, you know, maybe data points for each individual data point. Maybe that might be in an individual experimental trial, and then you plot the results just like. Okay, so this way, you know, with this, with this type of, you know, when you present your results in this way, when you characterize the results in this way, you can then generalize this as long as the non-dimensional numbers are the same, right? Then this result can work for any kind of rectangular geometry. Okay. All right. Any questions on this? Okay. Good. All right. So before we move on to pipe flow, you know, while we're still here in non-dimensional analysis, and this is actually a good segue because, you know, we'll be using some of these non-dimensional numbers in pipe flow as well. Let's talk about some common non-dimensional numbers that you see in fluid mechanics. Because as you've probably seen in the you know, in the past couple of examples that we did yesterday, there are certain non-dimensional numbers that kind of show up almost all the time when you talk about fluids. Okay. And that's not by coincidence, just because there are certain quantities and certain certain numbers that have a big influence on fluid mechanics phenomena. So we're only going to cover a couple of these today. But you know, one thing you'll see, and maybe this is the reason why we do dimensional analysis in fluids, is that fluids scientists and fluids engineers, they love their non-dimensional numbers. In fact, you know, there's a period of time which I think still persists to the present day, where everyone is kind of looking for the next non-dimensional number that is going to be a big thing, just because they want to name it after themselves. Because most non-dimensional numbers you see are named after the people who discovered them. Okay. Because that's really cool, you know, that's really cool to say that, oh, you know, let's calculate the Justin number, or let's calculate the Tran number. Then you're kind of forever immortalized in fluid mechanics lore, I guess you can say. Okay. All right, so the couple that we're going to talk about, one, you know, we've seen this already, and I've already been referencing it by its name, which is the Reynolds number. Okay. So this is probably the most common non-dimensional number that you're going to see in fluids, and you know, I cannot let you guys leave this class without knowing what the Reynolds number means, because it's you know, that important. Okay. So oftentimes you see it kind of displayed in the literature as RE. So RE stands for Reynolds number. Okay. And the exact definition. And so the interesting thing about these non-dimensional numbers, because they're non-dimensional, you can actually present it in two ways. You can present it as its reciprocal or present it on the forward way. Okay. So the way we've been kind of working with it, and this is just as a result of our application of Buckingham pi. So don't write this down just yet. But the way that we typically kind of display it is like the following. Right, we have the viscosity on top, we have the density, velocity, and the length on the bottom. But actually, if you look at how Reynolds number is traditionally defined, it's actually the reciprocal. of this. So traditionally, Reynolds number is the density times the velocity times some length scale divided by the viscosity. Okay. So this is really important. You know, and as you can see, it's shown up twice here, okay, in all of our examples so far, right? Because the Reynolds number, what we're going to talk about later today, this is how we essentially determine whether a flow is laminar or turbulent. So let's see. Which, you know, I realize those terms don't really mean anything right now, just because, you know, we haven't described what laminar means or turbulent means. You've probably heard of the concept of turbulence if you've ever flown in an airplane. Turbulence is what happens when, you know, the airplane goes through some rough air and it causes, you know, a lot of shaking and air sickness in the cabin. I get motion sick very easily, right? But, you know, that is kind of the main way that Reynolds number is sourced. Okay.
So it's to determine if it'll be smooth or chaotic, like.
Yeah. Mm-hmm. Yeah. So that's essentially the difference. So laminar flow is essentially kind of more smooth, kind of well-behaved flow. Turbulent flow is more kind of chaotic and rough. Yeah. And Reynolds number is the main way that's used to determine whether that's the case. All right. So how do we get here? So what is, you know, what does the Reynolds number represent? Because what you'll see is that, you know, all of these non-dimensional numbers, they have some interpretation. Okay. And the interpretation is always going to be a ratio of some kind. Right, so the Reynolds number, the way that you can interpret it is that the Reynolds number is a ratio of the relative strength of the inertial forces in the fluid flow versus the viscous forces. Okay. Right, and so another way that we can express the Reynolds number, right, it's a ratio of inertial forces or inertial effects, I guess if you want to be more general, divided by viscous effects. In fact, you know, if you think of all non-dimensional numbers as a ratio of some kind, you know, you would actually, you know, that would actually be a really great interpretation. Because one thing about a ratio, right, when you take a ratio between two different things, their units are always going to cancel out because you have the ratio of one thing and a ratio of another thing. They have the same units, so they cancel out. Okay, so most non-dimensional numbers that you see commonly in fluid mechanics is going to be a ratio of some kind. And what you basically interpret from that ratio based on the number, that's kind of the how you can interpret kind of some information about the flow. Okay. So as we kind of continue on with the rest of the class, the Reynolds number is going to be very important. So, you know, when we talk about pipe flow today, we're going to talk about Reynolds number and kind of what that means. And then when we talk about external flows next week, the Reynolds number will also be an impact as well, right? So when I make statements of, you know, let's say we say the Reynolds number is 100 or the Reynolds number is 1000, things like that, right? don't just take it as just like a number, right? So think of it as like a ratio. So, for example, right? So let's say if we have a Reynolds number of, let's say 1,000. Which is very common. It's not that hard to get a Reynolds number of 1,000, right? So one way we can interpret this is that for a flow with a Reynolds number of 1,000, right, the inertial effects, so the effects that have to do with, inertia, so that's velocity, momentum, density, things like that, those effects are 1,000 times as strong than any of the viscous forces that are in the flow. So I want you to think of your non-dimensional numbers like this, especially the famous ones, right? So especially things like the Reynolds number or the Mach number, right? So think of their values as like a ratio of some kind, okay? Because it goes the other direction as well, right? Right. So you can also have Reynolds numbers that are very, very low as well, right? So you can have a Reynolds number of, let's say 0.1. So this would be within the category of what I call creeping flow. So now creeping flows is not really a subject for undergraduate fluids. And so that's something you would learn in graduate school, just because creeping flow has its own kind of its own theory, right? But a Reynolds number of 0.1, at least on the surface level, you can say that for this type of flow, the viscous effects are 10 times as strong than the inertial effects. So again, we're not really going to be in that regime much in this class. In this class, we're mostly going to look at inertial dominated flows, just because first of all, they're just a lot more common, and also, they're a little bit easier to analyze. But just know that the other extreme happens as well. Okay, so Reynolds number, ratio of inertial effects to viscous effects, probably the most common, probably the most famous non-dimensional number you'll see in fluids. Okay. All right. Any questions on this, on the Reynolds number? Okay. All right. So the other non-dimensional number you'll see, and this is probably you probably heard this more in movies and things like that more than science, is the Mach number. Okay, so the Mach number, again, we can interpret the Mach number as a ratio, but Mach number has kind of a very interesting kind of interpretation. So the definition of Mach number is actually very simple. So the Mach number is the velocity of the fluid divided by c, where c here is the speed of sound. So it's basically just a ratio of two different velocities. Right. And then the question is, what does this represent a ratio of, right? And so the way we can interpret the Mach number is that the Mach number basically tells you the ratio of inertial effects versus compressibility effects. Okay. So the Mach number is very useful because for the most part and for the entire class up until this point, we've always assumed that our fluids are incompressible. right? And so the fluids, even though they may change shape, for the most part, they maintain the same volume. You have the same amount or same mass of fluid, right? But that's not necessarily the case when you get to very high speed flows. And so, if you end up working on, like fighter jets or airplanes or rocket ships, right? The compressibility of fluids starts to actually become relevant because the fluids are moving much faster at them. So until your fluid velocity gets up to that level of the speed of sound, you can assume that the flow is incompressible. And that's a fairly safe assumption. Okay. So the threshold here obviously is going to be, flows with a Mach number around 1. And so if your Mach number is, 0.8, 0.9, 1, 1.1, that's when you should start to consider compressibility effects. Okay. All right, but I think Mach number is fun to talk about with the under the context of the people often use it to describe the performance of high-speed jets. So I remember when I was growing up, the Concorde was the fastest plane on Earth. And so when an airplane can exceed the speed of sound, we say its Mach number is greater than 1. But Mach number is also used in a fluid mechanics context as well. All right, any questions on this before we move on to pipe flow? Okay, all right, so let's go ahead and move on to pipe flow. And so pipe flow is pipe flow is a little bit of a beefy topic. So we'll be covering for the rest of today and probably for the lecture tomorrow as well. So we are going to shift gears. Okay. So pipe flow is a very interesting topic in that I think this is probably as close as we're going to get to something that's, very directly applicable. Okay. Because up until this point, everything we've covered in this class, I would say is pretty heavy on the theory. But pipe flow is something that is very okay. Because we're looking at a very, very kind of niche, a very specialized situation, which is fluid flow within a closed conduit. And so even though this subject is called pipe flow, right? So normally when you think of a pipe, you think of a cylindrical pipe, but all this theory is relevant for any kind of rectangular ducts or anything like that. So as long as the flow is completely contained, it's in some kind of long tube-like structure, that I would consider that a pipe. Okay. All right, and so basically, whenever you have a situation where you need to move fluid from one location to another, most of the time you're going to transport it in some pipe. Right. So as you can imagine, this happens very commonly in engineering. Okay. Right. So you can think of any number of situations off the top of your head, right? So all the plumbing that occurs in a building, moving water from the main water line up into your faucet or to flush your toilets and things like that. All of that is flow through a pipe. You could think of your HVAC system, right? Air conditioning, heating, ventilation, right? That's movement of a different fluid, so that's the movement of air, but that's still movement of a fluid within a closed conduit. Okay. You can even think bigger than that, right? And so like the big oil pipelines that are used to transport oil from very far distances away over to our refineries, that's also flow in a pipe. You can even think microscopic as well. So you can think of the flow of blood through the blood vessels in your body. That's essentially flow in a pipe as well. Okay, so pipe flow, even though may sound kind of very niche, is still applicable to lots and lots of different subjects. Okay. All right, and so the whole kind of the goal with this section here is to kind of equip you guys with a set of equations and a set of tools to start to analyze these types of piping systems. Because oftentimes when you're designing a system like this, you're going to be asked questions of how big should your pipe be, how long should your pipe be, what type of flow rate should you use for them. Okay. So I want you guys, my goal here with this section is to kind of introduce, first of all, just the conceptual understanding and the topics that govern behavior in pipe flow, and also to equip you with the knowledge and tools to start to design these types of systems yourself. Okay. Because something that you would think would be rather rather routine, right? So just flow of liquid in a pipe, right? You'll start to see that there's a lot of complexity and a lot of nuance in terms of what you do, in terms of what you select. So, and we're going to kind of go through that today. Okay. All right. So to start, let's actually return to the topic of, that we covered, maybe 5 minutes ago, talk about the Reynolds number. Let's talk about the difference between laminar and turbulent flow, because that does make an impact in terms of how we design, how we analyze our pipe flow situations. Okay. So, like we mentioned earlier, like what Chris mentioned, typically a laminar flow situation is one where the flow is very smooth, very orderly, and not that much chaos expected. Right. So the way this term actually got its name, so laminar is a term that describes different laminae, which are different kind of sheets or kind of layers. And if it's, or think of like a croissant, right? So different the different layers of a croissant, you can think of those as laminae. And so when you have laminar flow, the flow, if you look at kind of pure laminar flow, it looks like kind of sheets of fluid that are all kind of very orderly, kind of moving together. And you don't have fluid that crosses one laminate to the next. Okay, hence the name laminar flow. Okay. Turbulent flow, on the other hand, is very disorderly, very chaotic, and you have kind of a lot of seemingly randomness in the flow. It's not pure chaos. It's not pure random. You could still have turbulent flow that still moves fluid within a bulk. There's still going to be bulk motion, but there's going to be a lot more kind of random fluctuations within that flow itself. Okay, so to illustrate this, one of the most famous experiments was run by the Reynolds guy himself. So his name was Osborne Reynolds, and what he did was that he had flow in a pipe. He basically had flow in a glass tube. Okay. So this was an experiment that was done, many, many years ago, but it's such a good, I think, illustration that it's still presented and talked about in fluid mechanics textbooks even to this day. Okay. So what he did was that he had a glass tube or glass pipe. Yeah. So basically you can see on the interior, you can look inside. Okay. And he had a bulk motion of fluid flowing through the pipe, right? So there is flow and it is going in a particular direction. So in both situations here, right? So on one hand, I'm going to draw or illustrate what a laminar flow looks like. And on the other side, we're going to do a turbulent flow. Okay. So in both situations, we're going to have a bulk motion of fluid. So there is going to be flow, okay, moving from one side to the next, right? The difference is in how much of velocity or how much flow rate is given, okay? Now to illustrate kind of the motion, what Osborne Reynolds did was that in both situations, he injected a little bit of basically food coloring into the flow, just so that we can observe kind of how that food coloring spreads out. Okay. Right, so if you inject food coloring, so let's say that we put a syringe, so let's say we have a needle, it's coming like this, okay? Right, and so let's say through that needle, we're going to inject the food coloring, okay, or a dye. All right, so a couple things are going to happen when you inject that dye. On the one hand, because there is bulk motion, because the fluid is moving from one end to the next, right, we do expect the dye to move along with the fluid itself. Okay. Right, so we are going to expect the dye to kind of move from the left to the right, right? But that's fairly obvious just because we have flow that's moving in that direction. Okay. What's interesting though is that, in addition to the bulk motion or in addition to the motion of the dye going from left to right along the pipe, we also saw some spreading of the dye as well. Okay. Now in the laminar case, the spreading was fairly small, right? And so basically you inject the dye here, you see kind of a little bit of spread. With this cone here kind of represents kind of the amount of dye that's in there. Okay. So there's a little bit of spread, but it's not too crazy. But for the turbulent case, right? So let's say that we have our dye here, our needle, right? We inject the dye in. What Osborne Reynolds saw was that the dye spread out a lot more. Now I've kind of exaggerated it a little bit here, and so just to kind of illustrate the differences, but there was a very noticeable change in terms of how much the dye was spreading out. Okay. Now that spreading out was due to the chaotic motions in the turbulent flow. So what Reynolds observed was that as the flow got more turbulent, as it got more chaotic, you had kind of more of these random fluctuations. That causes more, basically cross-stream motion, within the fluid itself. Okay. Right. So it was the first time that I think anyone had, I would say, kind of very clearly, illustrated or very visibly shown kind of what this chaotic motion actually looks like. Okay. But that wasn't the only contribution that Reynolds saw from this, right? He actually saw a very strong correlation between the velocity of the flow and the amount of turbulence that he observed, right? And so as he cranked up the velocity, right, what he saw was that the spreading or the turbulence got more and more severe, okay, get more and more significant. Right? In particular, Reynolds did actually use principles of dimensional analysis back then, as he tested this with different fluids, different pipe diameters, was that there is a non-dimensional number that characterizes how much turbulence or how much mixing that he saw, which he ended up naming after himself. Okay. Maybe that's why dimensional analysis is so ingrained with fluids, because such a pivotal experiment was kind of grounded within dimensional. Okay. All right. So what he saw was that our Reynolds number, which again was the density times the velocity times the diameter of the pipe divided by the viscosity. Okay. So what he saw was actually very interesting. There were very distinct thresholds of the Reynolds number that characterize, different flow regimes. Okay. And so what he saw was that if the Reynolds number was less than 2100, okay, then the flow was laminar. Right. So we had kind of very well-behaved flow. There's very limited spreading, in that sense. Okay. But if the Reynolds number was greater than 4000, this gave you very turbulent flow. So those two thresholds were very clear. Now, you might be asking what happens in between, right? So what happens when the Reynolds number is greater than 2100 but less than 4000? So in this regime here, the flow was kind of in between. And so it exhibits some aspects of turbulence, but it wasn't turbulent enough to be considered fully turbulent. So we called this regime transitional. So the flow was starting to change between laminar and turbulent, but it hadn't really gotten to the point of full turbulence just yet. Okay. And that's very common. And so what you're going to see is that, for different situations, there's going to be a very clear laminar regime, a very clear turbulent regime, and there's going to be kind of a weird in-between area where the flow is kind of exhibits characteristics of both. Okay. But this is actually a very interesting result that, a number like this can characterize so much about the flow, and that there's actually very clear threshold for this. Okay. All right. So these were the thresholds that Reynolds found for his pipe flow. And this idea of using the Reynolds number to characterize laminar turbulence is still something we use today. But, you have to be careful because the exact thresholds to determine laminar or turbulent are different for different flow geometries. Okay. So these numbers here are fine to use for pipe flow. But what you're going to see next week is that, when we apply the same idea to external flow, right? So flow over some flat surface out in the atmosphere, these thresholds are going to be different. Okay. Here. All right, but this idea of using the Reynolds number to characterize the turbulence is a theme that we're going to be talking about today. Okay, because whether a flow is laminar or whether a flow is turbulent, it actually is going to change its behavior quite a bit. And we're going to use different tools and different equations to handle those two situations separately. Okay. All right, any questions on this? Okay. All right, so next thing I want to talk about is this idea of pressure and viscosity. So one thing that's going to be very relevant for our pipe flow, which you may have picked it up already just because of how the Reynolds number is defined, is that viscosity is going to play a very important role in terms of what we are going to do. Okay. Now, think about how we've understood viscosity up until this point. So viscosity, we've talked about as basically acting like friction for fluid flow. So viscous effects are essentially going to dissipate energy within your flow, right? And that's especially relevant for pipe flow, where pipe flow you have flow that's contained within these, very tightly, very small walls, right? And generally speaking, the closer your flow is to some kind of solid surface that's flowing past, the more viscosity is going to play a role. Okay. So viscosity and pipe flow are kind of two things that kind of go hand in hand. So we cannot really escape viscosity when you're talking about pipe flow. Okay. Now, when you have viscosity and friction like this, you need energy to basically overcome that friction, right? And so just like an object that's sitting on a table, like right here, like that stapler, right? If we wanted to move that stapler from one end to the other, we do have to apply some force to it because we are overcoming the friction between that stapler and the solid surface. Keep saying friction, this should be viscosity. Okay. Right, so the flow needs energy to overcome this, and it's even more difficult for fluids, just because generally the faster your fluid is going, the stronger the viscous effects are going to be. Okay? And so in that sense, viscosity, that's where viscosity and friction kind of depart, right? So for friction effects, if you think back to your physics classes, friction has kind of two different modes. There's the coefficient of static friction, coefficient of dynamic friction, where dynamic friction is usually less. But for viscous effects actually get stronger as your flow is going faster. And so that's kind of one thing to keep in mind. Okay? So where does the flow actually get this energy from, right? And so if these viscous effects are always present, if these viscous effects are just constantly sapping energy away from your flow, then the flow needs this energy to come from somewhere. Okay. So the main place where fluid gets its energy from, in kind of the general sense, and so this, there's also other sources, but flow is mostly going to get this from the pressure. Okay? Okay. And so there's actually, a very strong correlation in terms of, how much pressure drops in a pipe flow situation to how much viscous effects are going to be there. Okay. Okay, so to kind of summarize this, let's say we have flown a pipe, right? We know that there's going to be some viscous effects, right? Right, and then maybe I should have drawn this at the beginning, but we have flow here that's going from left to right. Okay, so the viscous effects are going to oppose the flow, right? Because it's essentially acting like friction, right? But to drive the flow, we have pressure that's within the flow itself, right? And so what happens, what happens when you have fluid of any kind flow from one location to another along a pipe where there's friction, is that the pressure is going to drop. Right? So as fluid flows along a pipe, just the presence of viscosity is causing that pressure to drop. Okay. And so in some sense, you can think of the pressure drop, by measuring how much pressure drops from one end to another as a measure of how much energy it takes to push the fluid through that pipe. So if the pipe is relatively easy to push flow through, so let's say it's a brand new pipe, the surfaces are very smooth, there's not going to be a lot of roughness or viscosity in there, then you should expect minimal pressure drop. But if you're trying to push flow through an outdated system, let's say your pipes are from the 70s, there's a lot of rust and corrosion on the inside of the pipes. Viscous effects are going to be a lot stronger. Or if whatever reason if you're trying to push honey through a pipe, then you're going to have a very, very strong pressure drop in those situations. Okay. And so for that reason, one thing that we're going to be interested in a lot. So let's say you're designing a piping system for an engineering application, you're doing a calculation. Pressure drop is almost always going to be something that we're going to be interested in because that's something that we need to know because that tells us, maybe the strength of the pump that we need to apply. Okay. Okay. So in almost all the problems that we're going to do, I think actually in all the problems, right? Pressure drop is something that we want to find. Or there will be situations where the pressure drop will be given to us, right? So those will be situations where maybe we're designing a system and we're designing it to have a pressure drop of X, and we want to basically solve for the diameter or solve for the length that's going to accomplish that exact pressure drop. Okay. But pressure drop and pipe flow, two peas in a pot, they come together. And so, it's important for us kind of as we move forward that you kind of, really appreciate and kind of understand the significance of what the pressure drop actually represents. So, okay. So essentially the pressure drop just kind of measures how much energy it takes, for the fluid to overcome these viscous friction effects, in the flow. All right. Any questions on this? Okay. All right. So last thing I want to cover before the break is kind of the more simple case. So let's go through now that we kind of have we've kind of set the table for pipe flow. Let's look at kind of the simplest case that we can think of, which is fully laminar flow in a pipe. Right, so laminar flow, these are situations when the Reynolds number is less than 2100. Okay, so these will be, fairly gentle flows. So flows where the velocities are not that high. Right. Now, the nice thing about laminar flow is that, we basically figured out laminar flow pretty much completely at this point. And so, with laminar flow, there are very, I would say, concise and very easy to use formulas to compute things like pressure drop. Okay. Which may sound like a strange statement to have, right? And so everything we've covered up to this point, we've had formulas, and so why is having formulas such an accomplishment? Well, you'll see. So once we get to turbulent flow is very difficult to analyze. It's still very much an active area of research, kind of trying to understand turbulence a bit better, which is kind of cool, right? And so you really kind of get the sense that you're learning something on the cutting edge when you think about turbulence. But also kind of scary because we've been studying turbulence. Turbulence is not a new thing. We've been studying turbulence for hundreds of years now, and relatively speaking, I would say we've made a lot of great progress. But at the same time, there's still a lot that we don't know about turbulence too, which is kind of scary at the same time. But for laminar flow, we understand it. Laminar flow, we've got it pretty much figured out at this point. Okay. So for a very simple pipe with a fixed diameter and a fixed length. Okay. So let's say that we have a pipe that looks like this. Right. So our pipe has a particular diameter D, has a length L. Right. There is a fully kind of formed relationship, explicit relationship between the volumetric flow rate in the pipe and the pressure drop. Okay. Okay, and that formula is the following. So we have Q is equal to delta P, right? Where Q, remember, is our pressure, Q is our volumetric flow rate. Delta P, that is our pressure drop. Okay. And this is multiplied by I times D to the fourth power divided by 128 times the viscosity times the length. So you can see here that pressure drop and volumetric flow rate are directly proportional to each other. So we do have that proportionality constant, right? So that pi d to the fourth over 128 mu times L, right? So that tells you that, the pressure drop also scales based on the length and the diameter, right? But generally speaking, as you increase the flow rate in your pipe, then the pressure drop also increases as well. So that's, consistent with what we just talked about, where, viscous effects get stronger, the faster the flow is. So the more volumetric flow rate there is, the viscous effects are going to get stronger. So you need a higher pressure drop in order to maintain. Okay. Okay. All right. So this formula here is actually very famous, and so it is actually derived from an analytical solution to Navier-Stokes. Right, and so this formula here is credited to Poiseuille. It's actually credited to both him and his assistant, which is someone named Hagen. And so this is called the Hagen Poiseuille. I always forget how to spell Poiseuille. Well. Right, so flow in a pipe, given that it's laminar, we have an explicit relationship between flow rate and pressure drop, which is actually really good. Okay, so we can use this formula to compute pressure drop. Okay. Right, or you can go both ways. So let's say you have a pressure drop. This formula here will give you the flow rate, or if you're given a flow rate, you can use this formula, just invert it a little bit to obtain pressure drop. Okay. Now, another interesting aspect that can occur. So we've only just talked about pressure drop driving flow, right? You can also have pipes that are on an incline as well. Okay. So when your pipe is on an incline, you also have gravity that's going to be in effect. And gravity can either impede your flow. So let's say your flow is going uphill, or it can actually help your flow if your flow is going downhill. Okay, so let's look at an uphill situation first. Okay. So let's say that your flow is going uphill just like this. Right, where your pipe here makes a certain angle with the horizontal. So let's say that it's angled by an amount theta. Okay. Right, and so in this situation, we are going to basically just modify our Hagen-Poiseuille law to include a factor to account for this incline. Okay, so the modification is that we're simply just going to subtract a term here that has to do with the gravity of the situation. All right, so Q here is going to be equal to delta P minus rho times G times L times sine theta multiplied by the same factor that we had up there. So pi d to the fourth divided by 128 mu times L. Right, so when gravity is in effect, then we're going to modify our equation just like that. We also have the relationship with downhill as well. Okay, so let's say our flow is going down a hill. So let's say that we have a situation like this, where flow is going down that way. You have some incline angle there as well. Okay. Our formula for downhill looks very similar. It's just that instead of subtracting the gravity term, we're going to add to it. So those are the two modifications that you have to make for uphill and downhill flow. Okay, so these formulas are unfortunately as simple as it gets. So once we get to turbulent flow, things get a bit more complicated, but we'll get to that after the break. So last thing I want to do before we go to break is I want to do an example, just illustrate to you guys how to use these equations, just to kind of give you some additional context. I mean, these equations are not too difficult to use. It's just kind of plugging in, but I think it's useful to kind of see some context in terms of what they're used and how they can be helpful. Okay. So before we do that, are there any questions on these equations here? Okay. All right, so let's go ahead and jump into an example. Okay, so for this example, let's consider the flow of oil in a pipe. Okay, so our oil here is going to have a viscosity, dynamic viscosity of 0.4 Newton second per meter squared. And we'll have a density that's slightly less than water, which is common for oil. Okay, so the density here will be 900 kilograms per meter cubed. Right, and so we're going to consider the flow of this oil through a relatively small pipe. And so our pipe here will have a diameter of 2 centimeters. But the pipe is going to be very long. And so we're going to assume the pipe here is 10 meters long. All right, so to illustrate this, we have just a very simple situation. We have flow in a pipe like this. It's very thin, but also very long. Okay. And so we have oil that's flowing through this pipe, just like that. Okay. For the length of the pipe, it's 10 meters. Diameter is 2 centimeters. Right? And oil has its properties that are given in the Okay, so let's say that, for our particular application, we require a flow rate of at least 20 milliliters per second. Okay. All right, and we want to answer the following questions. And so there's four parts of this problem. But you'll see that all four parts are fairly similar. Okay, so first thing we want to ask is first thing we're just going to say, is the flow laminar or turbulent? Okay. Next, let's assume that our pipe is just purely horizontal. And so for a horizontal pipe, let's compute the pressure drop. So for that, we're going to use the Hagen-Poiseuille law that we just went over. Okay, next for part C, let's assume that our pipe is still horizontal, but let's say we measure the pressure at the inlet to be 200 kilopascal. All right, so based on that, let's compute the pressure at the outlet as well as the pressure at the middle of the pipe. Okay. All right, and then finally in part D, let's assume finally that our pipe is inclined, okay? And it's inclined and the flow is going downhill. Right? So part B is going to ask us, if we were to incline our flow going downhill, at what incline level, so at what theta, would we need in order for there to be no pressure drop? Okay. So for part D, we're going to solve. Okay, so four parts here, but you're going to see all four parts are fairly short. It's just kind of the one application of it. Part A actually might be the longest. All right, any questions on just the setup for this example before we solve it? Okay, all right, so let's go ahead and get solving. So we're going to start with part A, right? So part A is asking us whether the flow is laminar or turbulent. Okay. Right, and so the only way that we can determine whether the flow is laminar or turbulent is to compute the Reynolds number. Okay. Right, so we're going to use Reynolds number is equal to density times the velocity times the diameter of the pipe divided by the viscosity. Okay. So we have everything here, right? So we have the density, we have the viscosity, the diameter, those are all given to us in the problem, but we're not given the velocity in the problem, right? Instead, we're given the flow rate. And so first thing that we need to do, just like we've done, in our control volume problems, is compute the velocity from the flow rate. Okay. We have flow rate that's given. And what we know from our previous chapters is that flow rate is equal to the cross-sectional area multiplied by the velocity. Okay. And so to get the velocity, we're just going to take the flow rate, Q, and divide it by the cross-sectional area, where the cross-sectional area for the cylindrical pipe is going to be pi over 4 d squared. Okay. All right, so let's just go ahead and plug in the numbers here. So the flow rate that's given to us in the problem was 20 milliliters per second. Okay. Now, milliliters is kind of a strange unit. You may not be used to working with that, but 1 milliliter is equal to 1 centimeter cubed. And it just so happens that the diameter was given to us in centimeters as well. Right? So the diameter was given to us as 2 centimeters. So you can convert everything to meters at this point, right? So you can convert the flow rate to meters cubed per second, and you can convert the diameter to meters. That's fine. But if you're kind of savvy, you can see that both of these are centimeters. Let's do the calculation first, right? Because that's going to give us our velocity in centimeters per second. Then after that, we can convert to meters. So it's just a little bit faster. All right, so we do the calculation here. We get an average velocity of 12.73 centimeters per second, right? Because now our centimeters just has units of 1 or exponent of 1. And so this gives us a velocity of 0.1273 meters per second. Okay. So let's take this velocity and let's plug it into our equation for the Reynolds number. Okay. So Reynolds number is going to be the density. Density that's given to us in the problem is 900 kilograms per meter cube. Our velocity that we just computed is 0.1273 meters per second. Diameter was given to us in the problem as 2 centimeters, which is 0.02 meters. And the viscosity was 0.4 Newton seconds per meter squared, which is already in SI units. Okay. So we plug everything in. And what we get is a Reynolds number of 5.73, which you can see here is much less than 2100, right? Because 2100 was the cutoff as defined by Osborne Reynolds to be laminar flow. And so the flow here is indeed laminar. It's actually very laminar. So 5.73 is a very low Reynolds number. So that's good because we need the flow to be laminar. Otherwise, the equations that we just went over don't have any merit. Okay. All right. So let's go and move on to part B. Okay. Right. So for part B asks us to compute the pressure drop for this flow situation. Right. And so to do that, we're going to use our Hagen-Poiseuille equation here. Right. So our equation is Q is equal to delta P times pi d to the fourth divided by 128 mu times L. Okay. All right, so let's just simply rearrange this equation so we can solve for the pressure drop. Right, so we're going to multiply both sides by the inverse of that coefficient. And so we have pressure drop, 2, Q divided times 128 mu times L divided by pi d to the fourth. Okay. Right, so this is just simply just plugging in the numbers. And what we get is a pressure drop of 20,371.83 Pascal. Okay. We still have part C and part D, but it is 4:20, so I think it's time for a break. So let's come back at 4:30 and then we'll finish up this example and then we'll move on to turbulent flow in a pipe.
Oh, your response about the just look at the study guide feature wise, that's enough. As far as this, a lot of the study guide is mostly covers like the conceptual portion. As
Yeah.
far as like the free response portion, you just say it's like mostly based off homework.
So the study guide has a section for the problem solving questions as well.
Oh, okay.
But yeah, to answer your question, it's homework 3. That's what I'm got.
So like, I mean, anything from like homework 2, would it transfer for like sort of stuff like that? Or
So we do use Bernoulli's a little bit on the conservation of energy stuff, so that's kind of baked into the
like
stuff.
mostly like how it pertains to
Exactly. Exactly.
all right.
Yeah. Okay, it's 4:30, so let's go ahead and get back into it. Okay, so we've done part A, part B of this problem. So part A, we've kind of confirmed that the flow is laminar, which is good because if it wasn't laminar, we'd have no way to deal with it. Part B, we computed the pressure drop where we just simply applied our Huygens-Poiseuille formula to this flow. It's simply just a simple rearrangement of the formula. Okay. Part C, we go back up and scroll up to see what part C was asking us. Part C asks us Part C gives us an inlet pressure. So part C tells us that the pressure at the inlet is 200 kilopascal. And so it wants us to compute the pressure at the outlet and the pressure at the middle of the pipe. Okay. Okay. All right, so let's start with the outlet. And so this one's actually very straightforward because, what we're given or what we just solved for in the previous part. What we just solved for in the previous part is that the difference in pressure between the inlet and the outlet is about 20,371 pascals. By definition, this is the difference in pressure between the inlet and the outlet. So this is P1 minus P at the outlet. Where P1 is given to us in this part, P1 here is 200 kilopascal. Okay. Right, and so all we have to do to solve for P out is just simply rearrange this formula to solve for it. Okay, so P out will be equal to P1 minus delta P. Okay. And so we just simply plug in the numbers and just note that 200 kilopascal is 200,000 pascal, right? And what we get from this is about 179.6 kilopascal. Okay. So that is the pressure at the outlet. Now, the second part of part C asks us to find the pressure at the middle of the pipe. Okay. Now, this one's a little bit more tricky just because, we can't use the formula that we had above, or at least we can't use part B for this part here. Okay. So what we actually need to do, we need to do this actually in two parts. First thing is we need to first compute the pressure drop from the inlet to the middle of the pipe. Okay. Noting that, as you travel from the inlet to the middle, right, middle of the pipe is only halfway down. And so instead of using a length of 10 meters, we're going to use the halfway point, which is a length of 5. Okay. All right, so let's go ahead and apply the same formula. And so we have delta P is equal to Q times 128 times mu times the length divided by pi d to the fourth. Okay. But we're not going to plug in the full length. We're instead just going to plug in half the length, which is 5 meters. Okay. So we plug that in, and what we get is 10.2 kilopascal. Okay, so that's about 10,200 pascal. If you'll notice that it's exactly half of the delta P that we computed before, just because pressure drop varies linearly down the length of the pipe. Okay. Right, and then so to compute the pressure at the middle, we're just going to use the same formula that we had here. So pressure in the middle is going to be P1 minus delta P that we just computed right here. Right, and so pressure at the middle is going to be 189.8 kilopascal. Okay. So part C, part C, there's not too much, there's not much to part C. It's just, just illustrating to you what the pressure drop actually is. And if you're given an inlet pressure, which is not that uncommon, right? And so oftentimes, let's say that your pipe here is connected to a pump. A pump is going to essentially pressurize your flow up to a certain amount. And then you want to compute how much pressure drop that you have, going from that inlet to the outlet. Okay. That's very common because if you think about how piping systems are designed, let's say for common plumbing, right? Your fluid in your pipes is often raised by its pressure. And so, this will help you compute, what the pressure is at a certain point within your house. Okay. Okay, finally, part D. Part D is kind of the interesting one. So for part D of this problem, we're going to assume now that our pipe is flowing downhill, right? And we're going to incline the pipe enough such that gravity is going to provide all the work needed to overcome viscous friction. Okay. So the idea with part D is that if we incline the pipe enough, then the pressure doesn't have to change, or we don't need any pressure drop in order to drive the flow forward at the given flow rate. Okay. Okay, so for downhill flow, we have our equation for this. So we have Q is equal to delta P plus rho times G times L times sine theta times our other constant here, I d to the fourth divided by 128 mu times L. Okay. Great. So for part D specifically, it tells us that our pressure drop is 0. And so let's go ahead and cancel that out. Right? And so if we cancel out that delta P, then all we're left with is the product of rho times G times L times sine theta times pi d to the fourth divided by 128 mu times L. Okay? And so all we're going to do is we're going to solve this expression here for theta. Okay, so first thing we see is that both of these terms here have in length. Okay. So that is going to cancel out, which is an interesting result, which tells us that this result that we obtained here is independent of the length. Okay. So no matter how long our pipe is, it's not going to affect the incline under which we are going to solve for. Okay. And so we get Q is equal to sine theta times I d to the fourth times rho times G divided by 128 times the viscosity. I just rearranged the terms a little bit just to make things a little bit, easier for us to isolate things. Okay. All right, and so from here it's just simple algebra. So let's go ahead and isolate theta. So let's go ahead and multiply both sides by the reciprocal of that fraction there. Okay. And so we have 128 times Q times mu divided by pi d to the fourth times rho times G. This is equal to sine theta. Okay. Okay. We have everything we need to plug in on the left side of this equation because we have the flow rate, we're given the viscosity, we know the diameter, and we know the density of the flow, as well as gravity and pi and 128, of course. Okay. So we have everything there, and so theta here is just going to be the arc sine of everything on that side. Right? So we take the sine inverse or arc sine of both sides. Okay. So the arc sine and sine are going to cancel out, and so that gives us theta is equal to 13 0.35. And so actually it's not a lot, right? And so we don't actually need to incline all that much to drive the flow, which is good, right? And so this fact is actually utilized quite a bit in engineering as well. So if you can leverage gravity, right? If you can leverage some downhill flow to kind of help your flow rate and pressure drop, it actually saves you actually quite a bit of energy. So use gravity to your advantage. Okay. Any questions on the conclusion of this example here? Okay, good. All right, so that was a good warm up, right? So laminar flow, very nice to work with because we have these explicit formulas. In fact, the Hagen-Poiseuille formula for the most part gives us, everything we would ever need for pipe flow. It basically gives us a way to relate pressure drop and flow rate and the diameter. Okay. If this were the end of pipe flow, then we wouldn't be nearly as interested in it. Then it would be very easy to analyze. Unfortunately, a lot of pipe flow doesn't fit into the laminar category, and it does make things a lot more difficult to analyze. So let's talk about turbulent flow in pipes. Okay. So like I was talking about earlier, we compared to laminar flow, we actually understand very little about turbulent flow. Comparatively speaking, there's a lot that we've learned about turbulence up until this point, but overall, if you would ask me, overall, how much of turbulence do we understand in terms of predicting how turbulent flow forms and how the behavior actually is, there's still a lot to be learned. Okay. And that's illustrated no more clearly than how we analyze pipe flow problems. Okay. So for turbulent flow problems, right, we can't really rely on an analytical formula to solve for things like pressure drop and flow rate. Okay. Okay. The key word there being analytical. Okay. So all the formulas that we've covered so far, in this class, and honestly, probably a lot of the formulas you've learned in other classes up until this point, they have their basis in what I call first principles. And so what that means is that you can derive an equation analytically, just using just very basic concepts of force is equal to mass times acceleration, things like that. Okay. So those are what I would describe as analytical formulas, where you can take a situation and you can apply just very basic principles of conservation of mass, conservation of momentum, conservation of energy, and derive equations for that. Okay, so what we just covered with laminar flow in pipes fits under that category because the fundamental equation for fluid mechanics is Navier-Stokes, and through Navier-Stokes you can use that to derive the Hagen-Poiseuille formula. Okay, which we didn't do, obviously, just because we haven't talked about Navier-Stokes. We'll probably mention Navier-Stokes end of next week, right before the final. But there is a way to derive that. For turbulent flow, unfortunately, there is no analytical formula to do such a thing, just because of the randomness and chaos that come with turbulent flow. Okay, so for turbulent flow, our approach is going to change pretty significantly. Okay. And so for turbulent flow, in the absence of analytical equations, we have to make use of what's called empirical data. So you might have heard that term empirical before. So empirical basically just means experiments. Okay. So in the absence of equations that are derived from first principles, what we have instead is that we've had people that have run experiments and have run tests over the years, over the hundreds and dozens of years that we've studied this, and they've collected a bunch of data that they found to be consistent under certain situations. Okay. Now we can make use of this data, right? And we trust that this data was collected in a way that was very, that makes sense, that's correct, right? So we can use this data to actually perform our analysis. Okay. So it's a very different kind of way to approach these types of problems, but it is actually used a lot in practice. And if you get into certain areas of fluid mechanics where it is very difficult to analyze analytically, pipe flow being one of them, then you're going to get used to a lot of these types of data tables. Okay. In particular, if you get into the field of HVAC, which is heating, ventilation, air conditioning, that whole field kind of runs on empirical data. Even though I would argue that we have better tools now to analyze that type of flow. We have simulations, but engineers way before computers were a thing use data like that to perform their analysis, and it works. I mean, you can't really argue with the results. HVAC is a very reliable type of system. Okay. So we're going to get a little taste of that here today. Okay. And so in particular, we're going to make use of something called the Moody chart, right? Which is basically a collection of a bunch of different turbulence experiments to do our analysis. Okay, so the Moody chart is something that we're going to kind of work our way up to, but I at least kind of wanted to kind of introduce this idea in general. Okay. Okay. All right. So as a starting point, let's actually remind ourselves of something we talked about, last week when we talked about conservation of energy, which was the modified Bernoulli's equation. So remember, the modified Bernoulli's equation was our Bernoulli's, but we included terms to account for things like shaft work, right? So any kind of mechanical work that we're going to be inputting into the flow. So remember, we use that to account for things like like a pump or maybe like a turbine type like device. And we included a term for the losses as well. Okay. Now I'm going to present this in a very interesting kind of way, a form that we haven't seen just yet. So I'm going to take our modified Bernoulli and I'm going to divide the entire expression by the density as well as gravity. So this gets us a very kind of interesting form of Bernoulli's equation that I would say is kind of unique to pipe flow, just because of just mostly just tradition in terms of how pipe flow has been analyzed in the past. Okay, so we still have all the same terms, it's just that they're scaled a little bit differently in order to get everything in units of length. Okay. All right, so our modified Bernoulli is the following. So we have P 2. Let me call it P out. P out divided by rho times G plus V out squared divided by 2G plus Z out. Okay. So that's the main reason why we divide everything by density and gravity, just so that we can kind of isolate the gravity term just by itself. Okay, so that's just now just Z, so the height. Okay. So if you look at the units for everything here has units of length. And so this is equal to, same things at the inlet. We have P in divided by rho times G plus V in squared divided by 2G plus Z in. Okay. Plus two additional terms here. So we have HS minus HF. Okay, so this form of the modified Bernoulli here, we call this the pressure head form of Bernoulli. Where every term here, every term in this expression has units of length, or dimensions of length, excuse me. Okay. And there's actually a reason for that. It actually goes all the way back to manometry, if you kind of believe it. Okay. But another way to interpret actually the dimensions of this equation is that every unit, every term here has units of energy divided by weight. Okay. Which strangely enough, if you work out the dimensions of energy per weight, you just get length. Okay. So most terms here are pretty self-explanatory. We've brought up Bernoulli, many times throughout this class, and so we're not going to spend too much time on it. But I am going to focus on the last two terms of this expression, the HS and HF. Okay, so HS. Okay. HS is what we call the shaft head. Okay. So I know head is kind of a strange term to use here, but head is basically just the length. Okay. So think of this as kind of the think of this as a measure of the energy per weight in the fluid as measured by a manometer. That kind of makes sense. And so head is the origins of that term is that when you measured pressures or energies in a fluid, your manometer or something would go up or down by a certain amount, and we called that would usually be called head. Okay. So shaft head here represents the mechanical work that's done either on the fluid or done by the fluid. Okay. And so, again, if you had some kind of pump or turbine that is either inputting energy into the flow or extracting energy from the flow, this is where it would be accounted for. Right. So when we did conservation of energy in our control volume analysis, we put a lot of emphasis on this term here, just because that's how we extract or take energy in. But for pipe flow, we're actually going to put a lot of emphasis on the other term, which is the loss, head loss. Right, so that's HL. Right, so head loss is any kind of energy that is dissipated from the system through effects like viscosity. Okay, but there are other effects that can also sap energy as well. Okay. All right. And so when you have turbulent flow in a pipe, right, what we're interested in computing is, what are these head losses for that flow, right? And it turns out, and luckily for us, that there have been a lot of experiments and a lot of data throughout history that have gone in to quantify what the head losses are for turbulent flow in a pipe. So we are going to be relying on that data to compute these head losses, and then in turn use that to use our modified Bernoulli. Okay, because remember, normally for a Bernoulli equation, we can only use it for flow that is inviscid or flow that doesn't have viscosity. But modified Bernoulli, because we are including this head loss term, we can actually use it for viscous situations. So it's actually perfectly fine for us to use this. Okay. And Bernoulli's equation, luckily, is one that does not really rely on being laminar or turbulent. So we can use that here as well. Okay. Turbulence really messes things up. And so it really kind of prevents us from using a lot of other equations in fluids, namely potential flow. Potential flow does not work with turbulent flow. Potential flow, we have to have laminar flow. And I know I keep bringing this up, just even though we haven't talked about it yet, but Navier-Stokes as well. You really need to make a lot of modifications in Navier-Stokes in order for turbulent. Okay, so the fact that we have a tool like Bernoulli's equation, albeit in kind of this kind of strange form, this head form, the fact that we can use this for turbulent flow is actually a very big asset for us and one that we are going to take into account. All right, and so the plan for the rest of the class is to basically quantify this loss term and kind of talk about how we actually compute that, and then maybe do an example of two on how we actually do that. Okay. Okay. Any questions on this so far? Okay. All right. So let's talk about this loss term a bit more. Okay, so let's talk about losses in turbulent pipe flow. So head losses in turbulent pipe flow generally fall into two different categories. Okay. And I will say that the naming convention for these two categories is pretty terrible. And so I'll kind of work to kind of dispel that naming convention, but this is just what it's called, and this is what everyone calls it, and so we have to kind of abide by that. So the first category are what called major losses. So major losses are energy losses in the flow within straight sections of pipe. Right, and so in sections of pipe that have that go in a straight line, that have a fixed diameter, right, there's going to be pressure losses or energy losses due to that. Okay, we even have that in the laminar case. We just saw that in the previous example, right? So we call those types of losses major losses. The other type of loss is what's called minor losses. Okay, so major losses and minor losses. So minor losses are any type of energy loss or any type of head loss that occurs due to non-linear pipe components. Okay, so things like a turn, right? So when the flow has to change direction, it has to go by a 90-degree angle. Maybe the flow is going through a nozzle, maybe it's going through an expansion, right? All of those will incur some type of energy losses due to the turbulent flow that's associated with it. Right, so things like turns, narrowings, expansions, maybe you have a flow that's splitting into two different pipes, right? All of those will incur things like these minor losses. Okay, so because it takes extra energy to kind of go through those types of pipe components. Okay. Okay. Now the naming for this is terrible, right? Because it kind of implies that, major losses have, you incur more energy loss in the straight segments of pipe, but that can't be further from the truth, right? So in fact, for a lot of piping systems, let's say that you have a piping system that requires a lot of turns, right? The minor losses actually end up being greater, right? You end up having more energy loss from all the turns and narrowings and expansions than the straight segments, right? So the naming convention major and minor have nothing to do with the relative magnitudes in a particular piping system. So you're going to do problems. In fact, we're going to do examples, maybe not today, but maybe tomorrow, where, the minor losses, they are much bigger than the major losses. And that's very common, and that's very normal. Okay, so don't be alarmed by that. Okay. Okay. But both of these combine together to form the head losses in the fluid. Okay. So basically, our head loss term in our modified Bernoulli, HL, is basically just a sum of the major losses and the minor losses. Okay. All right, so what we're going to do is we're going to go through each one individually. So we'll start with the major losses. And so I'm pretty confident we should be able to get through that today. And then, we'll talk about the minor losses after that. Okay. Okay, but the only difference between major and minor losses are in terms of where they occur in a piping system. Okay, so major losses are only for straight segments, right? So segments that have no bends or turns, no changes in diameter. Okay, minor losses are essentially kind of everything else. Okay. All right. Any questions on this before we move on to major losses? Okay. All right. So let's talk about major losses and let's see what how we can compute them. Okay. All right. So major losses represent, again, the viscous energy losses in flows in straight segments of pipe. Okay. Now, if we were to do a dimensional analysis, we would obtain the following relationship between the pressure drop in a straight segment of pipe. So in a straight segment of pipe, so in a straight segment of pipe, the pressure drop depends on the following variables. Okay, so we have pressure drop is equal to a function of, right? So we're using kind of the same convention that we did yesterday for dimensional analysis, right? So we're saying that pressure drop depends on these variables. Okay, so it depends on the velocity of the fluid. That should be hopefully pretty straightforward to this point. It depends on the diameter of the pipe, depends on the length of the pipe. It depends on the viscosity of the fluid, the density, okay? And one additional parameter here for now I'll call epsilon, okay? So the pressure drop is a function of all of these variables here, which are 6, okay? So it depends on a lot, right? And it's so you can see for turbulent flow, this is a very kind of complex scenario that we're looking at, right? So even doing this from a dimensional analysis from an experimental viewpoint, it's not exactly an easy situation to look at. Okay. All right. So most of these variables we've worked with before, right? So velocity, that's been a constant theme in this class. Diameter and length are geometric properties, and viscosity and density, those are fluid properties that we've worked with a lot before. Okay. That last parameter there, epsilon, this is what's called the surface roughness. Okay. So surface roughness is a parameter that describes, how rough and coarse our pipe surface is that's bordering our fluid. Okay. All right. So specifically, the surface roughness has a dimensions of length. So if you have a typical pipe here, right? So normally, if you've used a pipe pretty significantly and it's been in operation for a while, there's a bunch of, either rust or corrosion that gets kind of built up on the surface. Okay. Even for brand new pipes that were, let's say we've machined a pipe out of metal, right? Just by the machining process, it's very difficult to get a very smooth and kind of, very smooth surface on the interior. Okay. So almost always there's going to be a little bit of kind of coarse graininess on the surface of the inside of the pipe. And of course, I'm kind of exaggerating it here a little bit, and so it's usually not this noticeable. Okay. But that surface roughness basically tells you the peak to peak amplitude of that kind of graininess that we experience. Okay. And so if you kind of take, maybe the difference between the height, top and the bottom here, that is epsilon. Okay. So that epsilon, you can think of it as kind of a measure of the unevenness of the surface. Okay. So surface roughness is something that you can look up. So generally for relatively new pipes, assuming very standard machining procedures or manufacturing procedures, this is something that you can look up. Okay. So actually, if you look in the textbook, and I will say I haven't gotten a recent version of this textbook in many, many years, but in the version of the textbook that I have, which I think is from 2000, from like 2000, I think it's like 2011, when I took fluid mechanics as an undergrad. This was table 8.1 in the textbook, so I assume it should be the same, assuming the chapter numbers are the same. But this is something you can look up online as well. Okay. So so this is kind of our first taste of, um, you know, using something that's not an analytical equation, that's not something that is derived first principles to assist in our calculation. Okay, now how is this surface roughness used? Well, this surface roughness is used in combination of other experiments that are quantified in something called a Moody chart. Okay. Okay. So the Moody chart is something that, it basically is a summary of a bunch of different turbulent pipe experiments that is presented in a way that you can use conveniently for your calculations. Although, the first time you see it, it may not seem very convenient. Okay. So I'm going to do my best to kind of recreate it here, but this is definitely something that you should look up yourself. It is in the textbook, but Moody chart is also a very standard engineering chart, and so there's probably dozens of different versions of this that you can just search for the internet. Okay. So the Moody chart looks like the following. So it's basically a chart. It's like this. So on the horizontal axis is the Reynolds number, right? And so your friction or your amount of head losses here, like we discussed, depends on the Reynolds number. So that is your unit down there. And you want to be careful using this because the Reynolds number on the horizontal axis uses a log scale here, right? And so instead of being a linear scale, it's scaled logarithmically. So that means we have one, each tick mark goes up by an order of magnitude. 3rd, 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, okay? Even goes all the way up to 10 to the 8th, so that is super turbulent flow, okay? Which does exist, right? So 10 to the 8th Reynolds number it sounds very large, but you know, those types of systems do exist. Okay. All right, and then what you're going to see here is that you're going to see various curves of different curvature that are kind of all overlaid on top of each other. Okay. So for instance, you know, we have one that maybe looks like this. Maybe another one that looks maybe something like this. See that. Okay. So the Moody chart kind of follows this trend that's like this, right? So this drawing is not perfect, and so you know don't take this, don't use this for your calculations here. But I'm just kind of showing you kind of the general trends here. Okay. Now, what do these different curves here represent? Each of those different curves represent a different ratio of the surface roughness to the diameter of the pipe. Okay. Right, so depending on that ratio, depending on the ratio of the surface roughness to the diameter, you're going to pick a different curve on the Moody chart. Okay, so let's say for instance, this top line here has a ratio of 0.05. Okay, so if the ratio of your surface roughness to diameter is 0.05, which is actually very rough, then you would use that top curve there. Okay, and then from there it goes down. Right, so as you go down here, you get to smoother and smoother pipes. Right, so let's say this is like 0.02, right? This is like 0.01. That's you. Okay, this might be 0.001. Okay, this might be 0.0005. Okay. So as your pipes get smoother and smoother, as your epsilon gets you know, less and less, then you're going to move down the Moody chart. Okay. The bottommost curve on the Moody chart is what we call a smooth pipe. So those are pipes with, you know, very, very little surface roughness, or, you know, at least, you know, that we can't determine. So that might be a brand new pipe that was machined very carefully so that the inner surface is very, very smooth. Okay. Whereas, you know, a very, very rough pipe, you know, maybe a pipe that's been there since the 70s or 80s, you know, has a lot of corrosion and has a lot of rust that's kind of built up. That might be somewhere near the top of the Moody. Okay. Now, what's interesting here is that, you know, you can see that the surface roughness by itself is not significant. What's actually significant is actually the ratio of the surface roughness to the diameter. Okay, so that's something to be careful. So you may have a pipe that has a very rough surface, but if it's a very big pipe with a very big diameter, that kind of, you know, cancels it out. Okay. Okay. And so the way to use the Moody chart is you're going to first find which curve that you're going to use depending on the ratio of epsilon over d. Then you're going to go to a different spot on the curve depending on your Reynolds number. Okay. So let's say that, you know, we're working on a pipe, you know, maybe it has a surface roughness to a diameter ratio of 0.01. Okay. And let's say that we have a Reynolds number of 10 to the 5th. Right. So let's say that gives us that location there on the Moody chart. So what does that tell us? Right. So if we follow this point all the way to the y-axis, okay? On the y-axis of the Moody chart is something called the friction factor, F. Right, and then there are numbers and tick marks on that vertical axis that tell you what the friction factor is. Okay, so the goal of the Moody chart is basically, you know, once we have everything from the problem, right? The goal of the Moody chart is to obtain the friction factor for your particular pipe example. All right, and then once you obtain the friction factor, there is a correlation between the friction factor and the head losses in a particular pipe. Okay. Okay, so once you find the friction factor, basically you can compute the major losses from there. Okay, so the formula for this is HL major is equal to friction factor, F, okay, multiplied by the ratio of the length divided by the diameter, multiplied by B squared divided by 2G. Okay. So once you have the friction factor, by using the Moody chart, we're basically making use of all the experiments we've done before. You can very easily obtain the major losses in a pipe flow that is fully turbulent. Okay. Okay. So I know that was kind of a lot of information, and so I do have an example where we're going to illustrate how to use the Moody chart. Okay, so we'll do that next. But before that, are there any questions on any of this? Okay, all right, so let's do an example just to kind of illustrate how this is used. Okay. All right, so let's consider air that is flowing through a very small pipe of 4 millimeters diameter. Okay. All right, and let's say that it is moving through with an average velocity of 50 meters per second. Okay. All right, so for this particular pipe, right, let's say that the surface roughness is 0.0015 millimeters. And let's say that we are considering a section of pipe that only has a length of 10 centimeters, or in other words, 0.1 meters. Okay. Okay. So assuming all those things, let's compute the pressure drop in this pipe, assuming the flow is turbulent. Okay. All right, so we have our first kind of case here where we have turbulent flow, right? We know that there's going to be a pressure drop just because viscosity is present. And so that's going to sap energy away from the flow. In fact, this flow here is moving very fast. And so we do expect there to be pretty significant head losses associated with that. Okay. Okay. All right. So let's go ahead and get started. So first thing we need, and always a good place to start, is we need the Reynolds number. Right. First of all, we need to confirm that the flow is indeed turbulent. But also it's a good idea to compute the Reynolds number just because we're going to need it for the Moody chart anyway. Okay, so Reynolds number, always a great place to start. Okay. All right, so Reynolds number, remember for a given flow is the density multiplied by the velocity, multiplied by the diameter, divided by the viscosity, okay? Now, the viscosity and density weren't given to us explicitly in the problem, but we know that we're working with air, okay? And so air, the density and the viscosity of air are very well documented, okay? Okay, and so if we plug everything in, right, we plug in the velocity and diameter from the problem, we plug in the standard density and viscosity of air, we get a Reynolds number of 13,700. Which is indeed turbulent, right? So remember the conditions for turbulence in pipe flow is that as long as the Reynolds number is greater than 4,000, then we have turbulent flow. Okay. So that's good, right? And so that means that we can use our Moody chart, okay? Or maybe it's bad news because that means we have to use the Moody chart, which is a little bit more inconvenient than using our formula. Okay. Okay, so let me scroll back up to the Moody chart and let's see what information we need in order to compute the friction factor for this problem. Now, this example will seem a little bit hand-wavy because I don't have the explicit Moody chart in front of me, but I will kind of show you how you would use it to obtain your friction factor. Okay, so let's scroll back up here. Let's look at our Moody chart. Okay. Right, so we just computed our Reynolds number. So our Reynolds number was 13,700. Right, and so we put that in scientific notation. Right, that gives us a Reynolds number of 13,700 is 1.37 times 10 to the fourth. Okay. So we're not that turbulent, right? And so the Reynolds number you can see goes all the way up to 10 to the 8th, but for Reynolds number of about 10 to the 4th, we're about here. Okay. So we're going to look for a friction factor around this line right here. Okay. Now the question is, which curve do we follow in order to compute our friction factor, right? And then to determine that curve, we have to determine the ratio of the surface roughness to the diameter, right? Okay, so let's go ahead and compute that as well. Okay, so the ratio of the surface roughness to the diameter here is our surface roughness as given in the problem is 0.0015 millimeter. Okay, so this is a fairly smooth pipe. Okay, and our diameter in this problem was 4 millimeter. Right, and so this gives us a ratio of 0.000375, which is unitless because we have millimeter divided by millimeter, right? Right, so you can kind of see that again, we're making use of non-dimensional numbers in a problem like this, which is pretty common because again, we're using empirical results, which are almost always presented as non-dimensional numbers. Okay. Okay. So now that we've computed our ratio of surface roughness to diameter, we need to go back to the Moody chart and find the curve here, which has this exact ratio. Okay. Right, and so once we identify which curve has that value of epsilon over d, that's the curve we're going to follow along with our Reynolds number to give us our friction factor. Okay. Now, the issue is, and you're gonna run into this issue a lot when you're doing problems, is that there's not gonna be a curve that matches your ratio exactly, right? And so if you look at the real Moody chart, there's no curve that matches a ratio of 0.000375 exactly, okay? So you're gonna have to kind of go to the closest one. Okay. Right, and so luckily for us, we're not that far off from an actual curve. And so if you look at the Moody chart, there is a curve for epsilon over diameter of 0.0004. All right, and so if we do that, we plug it in and we look at our Moody chart. Right, and so we go back up to our Moody chart, right? So let's say, I don't have it here, but let's say that we have a curve that's kind of in the middle here, or 0.0004, right? We obtain this point right here. We go to the vertical axis and we read the friction factor off that chart there, okay? And so what we obtain from this, you look at the real Moody chart, you get a friction factor of 0.028. Okay. Okay. So now that we have our friction factor, we can then compute our major losses using this equation right here, right? All right, so we have friction factor equal to 0.028, okay? Then that means our major losses equal to, we have friction factor multiplied by the ratio of the length divided by the diameter, multiplied by v squared over 2 over 2g. All right, good. And so everything else in that formula for the major losses we have, right? Because we're given the length of the pipe, we're given the diameter of the pipe, we're given the velocities, and we're given gravity. Of course, we're assuming that we're running this test on Earth. Okay. So now we can take this and we can plug it back into our modified Bernoulli equation to solve for the pressure drop. Okay. All right, so let's write out our modified Bernoulli one more time, right? And then let's solve for P out minus P, or P in minus P out, okay? Okay, so our modified Bernoulli has the following form here. So we have P out divided by rho times G plus V squared out divided by 2G plus Z out 2 V in divided by rho times G plus V in squared divided by 2G plus Z in plus our shaft work minus our head losses. Right. Now, just like normally, right? So normally when we write the Bernoulli, we're going to cancel out a lot of these terms, okay? And so even though it looks intimidating here, most of these terms are going to cancel out. All right, so first thing we're gonna say here is that because we're not given any information that our pipe is going uphill or downhill, there's no change in elevation, and so we can say that the height is not changing, okay? So Z out and Z in are the same. Okay, so they're gonna cancel out. We're also not told in the problem that there's any kind of pump or there's any kind of turbine. We just have a straight segment of pipe, right? And so there's going to be no shaft work. Right, so we just have basically just pure flow in a pipe, right? There's nothing that's adding or taking away energy from the flow besides viscosity, which we just computed, right? Another thing that we're going to cancel out, you know, and this is a term that we don't usually cancel out, is actually the velocity terms, right? And the reason for that is because in the problem, we're told that the pipe has the same diameter all throughout. Okay. Right, and then even though it wasn't explicitly told in the problem, but we can assume that the flow is steady state. We basically assume that all the time in this class. Unsteady flow is kind of a much more difficult beast. Okay, so if a pipe or if a system has steady flow and there's no change in diameter, right? Then by conservation of mass, that means the velocity must be the same everywhere throughout the pipe, right? Otherwise fluid would accumulate within the pipe or might deplete. Okay. And so that's going to be very common in these pipe problems. And so, we're not going to consider expansions or contractions until we get to minor losses. But if you're talking just major losses, which is a straight pipe with the same diameter, that means velocity in has to equal velocity out just by conservation. Okay. All right. And then all we're left with is just everything here, right? And so we have E out divided by rho times G is equal to E in divided by rho times G minus the head losses. But the head losses we have an expression for, which is up there. Okay. So let's go ahead and plug that in. We have F times L over D times E squared divided by 2G. All right. So from here is pretty straightforward. And so the pressure drop in this situation is just going to be P in minus P out. So let's go ahead and isolate that. So let's multiply both sides of this equation by the density times the gravity. So that's going to cancel out the denominators on both of the pressure terms. Okay. Let's move P out to the right side of the equation. Let's move the head losses term to the left. Okay. And then what we get is F times L over D. Right, we multiply that by rho times G. The G's are going to cancel out. And so we have rho V squared divided by 2 is equal to P in minus P out, which we know is equal to the pressure drop, delta P. Okay. All right, and so we have everything here. We can just plug it all in, right? So the friction factor we obtained from the Moody chart. We have the length and diameters given to us in the problem. Density of air we can look up in the table. Velocity is given to us in the problem. And so we plug all that in. We get a pressure drop of 1.0 0.076 kPa. All right. Any questions on that example there? Okay, good. All right, so before we get to the minor losses, I do want to mention a few other things. Okay. Okay. So for the most part, this Moody chart method is mostly used to compute pressure drops and friction factors for turbulent flow. Just because, we just don't really have any other alternative for turbulent flow. We have to use a Moody chart just because there's no analytical formula that we can use. Okay. All right, but if you wanted to, you could actually use the Moody chart for laminar flow as well. Okay. Right. So actually, if you look at the Moody chart in your book or just online, you'll see that there's a section of the Moody chart that I did not draw. Okay. And that pertains to the laminar section. Okay. So if I go back, let's go back up to the Moody chart just very briefly here. Okay. So there's actually a section of the Moody chart that you may have picked up on. You may have been wondering, why did I leave that section on the left so empty right there? Okay. Because that right there is the laminar section. So actually there's another part here which actually just kind of looks like a straight line, where this is the laminar portion of the Moody chart. And so if you want, even for laminar flows, you can use this Moody chart method to compute the pressure drops. Let's say that you only want to learn one method, you can just use this instead of using a separate set of equations for laminar flow, right? So normally, if you had laminar flow, you would use the Hagen-Poiseuille equation that we talked about earlier in the lecture today. But there is a section of Moody chart that you can use for laminar. Right? Also, this section of the chart here, there actually is an analytical formula for the friction factor. Okay? Right, so you don't even have to look at the chart. You can actually just use this formula, which is a lot easier to do. Okay. Right. So if your Reynolds number is less than 2100, which is for laminar flow, then the formula for the friction factor F is equal to 64 divided by the Reynolds number. So what you can do instead of using the Hagen-Poiseuille equation is that you can just use this formula for the friction factor, use this to compute the major losses, and use the major losses in Bernoulli to compute the pressure drop. Okay. Right, so there have been semesters, there have been times that I've taught fluid mechanics where I don't go over the Hagen-Poiseuille equation, just because this method here you can use for laminar flow as well. But actually, if you did use both methods, and so if you're ever curious, you could try using both the Hagen-Poiseuille method and the Moody chart method. You'll actually be surprised. You'll get some results that are actually conflicting, and so you may get a certain pressure drop with Hagen-Poiseuille, and you'll get a different pressure drop with the Moody chart. Which is very interesting, and that's not meant to be confusing. It's just the methods that were developed to for these two types of approaches were developed very, very differently. So Hagen-Poiseuille was, like I mentioned before, was developed based on first principles, and so just conservation of mass, conservation of energy, conservation of momentum, whereas the Moody chart was done purely empirical. And so Moody chart is just all experiments that people have done to compute this. Okay. Now, I won't give my opinion in terms of which one is better, just because there's people who think the analytical way is the truth, and some people would think that the experimental way is the better way. I think the real answer is that once you kind of start to get experience with these and kind of recognize other nuances in terms of how pipe flow develops and how it's used, you'll start to get a sense of which method is better in different circumstances. Hagen-Poiseuille, the analytical method, does rely on more assumptions, I would say. And so, if your flow is more, I would say, a little bit more textbook in terms of how it develops and its velocity profile, I think Hagen-Poiseuille will give you a more accurate solution. But I would say for more practical situations, maybe the Moody chart method will be a bit better. I just said I'm not going to give my opinion, but that was my opinion. But and so, but for this class, both methods are valid. It's just be aware that you may get conflicting answers. Okay. Another thing that I want to mention here is that turbulence is not just a factor of the Reynolds number. It is possible to get turbulent flow with low Reynolds number. Which is a statement that kind of seems to contradict everything that I mentioned earlier today, where Reynolds number is kind of the end all be all determination of laminar or turbulent flow. Okay, but turbulent flow, if you kind of really think about it, turbulent flow is characterized by nothing more than just kind of chaotic, swirling, seemingly random flow that does things like enhance mixing and has a lot of cross stream motion. Okay, so you can get that even in low flow situations. Where what you can do is you can do what's called trip the flow. Okay, so what you can do sometimes is that you can add some kind of roughness in the pipe on purpose to basically induce turbulence at low Reynolds number. Okay. And so this concept of tripping turbulence is something that we'll actually return to as well, right? And so when we talk about external flows at the beginning of next week, this is something that is done as well. And there's practical reasons for it too. Turbulence is not just, well, it is chaos, but sometimes chaos is good because what chaos sometimes does is that it also enhances mixing, right? And so if you have like a heat transfer situation where you're trying to extract heat from a surface, the turbulence will actually help. Right, so turbulence will actually help enhance that heat transfer, and sometimes that's what you want, right? So let's say you're designing, let's say a fin, or like you're trying to offload heat that's generated from an engine, right? Turbulent flow is actually better in that situation, just so that you can cool faster and you can kind of push more output from your engine or your computer or something. Okay. All right, but from a fluid mechanics perspective, when you intentionally trip turbulence, this is what's called wholly turbulent flow. Right, and so when you have wholly turbulent flow, it's actually interesting. Your friction factor in that regime does not depend on your surface roughness. So it doesn't really matter what the surface roughness in your pipe actually is. Your friction factor is going to be determined just by the fact that you're wholly turbulent. And so for wholly turbulent flow, this is kind of a separate thing. And if you look at kind of the real Moody chart, you'll see that there is a curve specifically for wholly turbulent flow. So if you're looking at the Moody chart, you're wondering what that curve for wholly turbulent flow is, that's what it means. Okay. And so another kind of interesting application for this is that, if you are designing a piping system that is designed basically to operate with very little maintenance over the years, right? What tends to happen in these long-term piping systems is that a lot of rust and kind of corrosion and kind of crud kind of gets kind of caked on the inside of these pipes. Okay, and so these are situations where the surface roughness is going to change with time. And so if you want the performance of your system to be independent of that kind of corrosion type process, then maybe you think about intentionally tripping turbulence so that your performance is kind of more consistent over the years, where you're in this kind of wholly turbulent regime instead of having something where the roughness is changing with time, and you're kind of moving up the Moody chart as a function of time, which is going to require more maintenance and kind of more constant. Okay, any questions on any of this? Okay, all right, so that's all the time we have for today. And so tomorrow we are going to take our midterm first thing. And then after the midterm, we will talk about minor hosts. Okay, all right, so thank you guys for coming today. Hope you guys have a good rest of your day. If you have questions about the midterm, I do have plans this evening, but I will be back working early tomorrow morning. So just send me an email or come to office hours and I can help you guys. Okay, so best of luck studying. Have a good evening, and I will see you guys all tomorrow. Okay. Yeah.
So, in theory, one way it is true, but either that it's where, since the dimples have the surface area, so
Mhm.
the airflow will be slower on the surface, right? So
Yeah.
therefore, which slows the air will go around it,
Mhm.
so therefore making it go faster.
Yeah, so that actually, so I got a bit confused because when we were going over the Magnus effect, I thought I would look dimples too. But actually, we'll talk about dimples on golf balls specifically next week.
Next week.
Actually, so when we talk about external flow, but those dimples are basically doing something like this, where they're intentionally tripping, or you're manipulating the turbulence.
Yeah.
So that you, because a golf ball is kind of flying through the air at very high speeds. And so to help the ball travel further with less drag, basically it helps to have the boundary layer stay attached to the ball as much as possible. And the dimples kind of help with that.
So with that, would it be better to have dimples on a car? So like the intake manifold would better to have the dimples on the inside. So I've seen people do it, but they didn't really get the data if it actually works or not. So
that's one way to kind of manipulate it, because if you can manipulate the flow to be turbulent, then you have actually a better control. It's actually easier to manipulate turbulence than it is to manipulate laminar flow. It is possible to get laminar flow, but you have to have a flow straightener, which people do as well. But yeah, what I'm guessing, I haven't heard of actually people using dimples on like a manifold on a car, but that's what I'm assuming that they're doing. Is they're kind of manipulating the turbulence to have a certain Reynolds number, a certain value, just so that they can kind of design it.
and I don't know if we talked about like velocity and pipes and stuff yet, or because I was thinking on a car exhaust, if we go from let's say 2-inch pipe and then turn to a 4-inch pipe, would it make it flow better, or should we just keep it consistent all the way through?
It would lower so you would introduce some minor losses in that point. And so you have basically a change in diameter. And so there are going to be some losses because there's going to be some turbulent flow where there's going to be some recirculation there. And so that does introduce some things. But if you look at our formula for the major losses here, right? Major losses also, we have the scaling based on the diameter down here, right? And so you increase the diameter, you reduce the major losses. So your minor losses go up, your major losses go down. So it's not as simple of an explanation to say like one is better than the other, because it depends on a lot of other things. But there are certain things that are kind of competing that are going on at the same time.
So would we to use this to let's say, because from the engine to the connecting pipes, it would be like a 1-inch or 4 1-inch pipes connecting to 1 2-inch pipe and then goes out the rest.
Yeah.
So can we use that formula to
Oh yeah. Although I would say that generally for air, I don't think viscous friction is that big a factor in that situation, because you're basically outputting to just atmospheric air at the end.
Yeah.
And so, it's not going to be, I don't think the losses are going to be that high if it's air.
Because I think it's more, I was trying to figure out a way how to make it more use the vacuum of it to pull up exhaust faster.
Oh, I see.
Therefore, creating more inflow of fresh air into the actual engine.
Got it. Yeah. So in that case, having a larger outlet there is going to help, just because there's less kind of constriction. And so you kind of you go into like a 4-inch, then you have more atmospheric air that's exposed to it. Then you kind of create a larger wake, which is going to suck more air out of that. So
And then another part is like where instead of doing like just a 2-inch to 4-inch, would it be? Is there any side effects of having a straight 4-inch all the way out? Where it's like bigger flow, but it reduces the pressure and slows it down because it's a lot wider now.
Because you're still going from 4 1-inch to now a 4-inch, right?
Yeah.
So that would increase your minor losses too.
Okay.
And so so we'll talk about minor losses tomorrow. And so I think that'll be because you don't want to have that big a dramatic kind of change in area all at once, and then that introduces a lot of losses.
So it'd be better to be like a 4 1-inch pipes into 2 1-inch pipes and into 1 4.
In theory, yes, yeah, because you want to be a bit more gradual in terms of how you change your area.
Okay. All right. Thank you.
Yeah.
Then first,
What's that?
there's a question on the homework.
Yeah.
For this one, the jet ski one.
Yeah.
So I got everything but a positive for us because I was thinking like you're expelling mass to the left.
Yeah.
Standard coordinate system. What if your torque speed going all the jets?
Right. So remember, whenever when we're using Reynolds transport here, we're computing the force that's on the fluid.
Oh, it's well.
But then the force that's put on the jet ski is opposite of that, right? And so the force on the fluid is going to the left, negative direction. But then the force that the fluid puts on the jet ski is
It's from the fluid's point of view.
exactly.
Okay, not the literal jet.
Exactly.
Okay.
Yeah. It's always I think that's the part that's confusing for people too. That when you use this, it's always the force that's on the fluid. And then whatever the force on the fluid, equal and opposite is going to be on the solid.
For the torque one to this one here.
Yeah.
I didn't do the Reynolds, I just did typical statics without the stat, I mean.
Yeah, you'll get the same answer. So honestly, for angular momentum, we didn't have a lot of time to go over it.
Mhm,
And so, if I do give you something, it'll be something very simple like that.
mhm,
And so that's fine for that. Yeah, we only had like 20 minutes to cover it. So
mhm.
yeah, I'm not gonna expect anything crazy for that.
I just had a question for we're doing the head loss and plugging it into the, modified Bernoulli.
Yeah.
You said V in equals V out.
Yeah.
Then wouldn't the head loss cause the V in or the V out to be less?
No, it has to be the same because remember, conservation of mass means that the velocities have to be the same.
Mhm.
Because if your velocity is less at the outlet, but your velocity is more at the inlet,
Mhm.
then you're gonna have mass accumulating in your system, right? Because there's not as much coming in, coming out. So the losses actually occur in the pressure. So that's where the main losses are going to be.
Really? So it doesn't affect like at all the speed or anything?
Nope.
That's weird.
Yeah.
That's interesting.
Yeah, it is kind of weird to think about, but think about it like, like if you do have a change in velocity, right? So let's say like if you can put numbers on it, like you have 10 meters cubed per second coming in and only 5 meters cubed per second coming out.
Mhm,
That means every second you have an accumulation of 5 cubic meters somewhere in your system.
mhm,
And eventually that has to go somewhere because mass can't be destroyed.
mhm.
And so, the velocities have to be the same at the inlet and outlet. If the diameters are the same. If the diameters are different, then you could have different velocities. But what has to be the same is the flow rates at both places.
But the pressure also, you have the pressure drop.
Exactly.
Because it just seems weird. I don't know. It's like, so it's going at the same speed,
Yes.
but then at the end you get more pressure.
You get less
More
pressure.
pressure. Sorry.
Yes.
Yeah, because it's a pressure drop.
Exactly. Yeah.
So that pressure goes in. Where did the pressure go that drop from the heat, the loss?
Exactly. So that pressure energy goes into heat. So that was dissipated by the viscosity, basically.
Because pressure is just like the average force on the surfaces, correct?
Yes. Yeah. Yeah. So you do have a net force when you think about it that way. So you have higher pressure at the inlet and less pressure at the outlet. And so you have a net force that's pushing it this way. Then that net force is being used to overcome friction.
Oh, that makes sense.
Yeah. So if you think about it, right? So like in order to move this stapler, right, I have to put a net force on it to overcome friction.
Mhm,
And I have to keep pushing at it, otherwise it's going to stop
mhm.
because of friction, right? So it's the same with the pressure. So it's the same with fluids. It's just that the thing that's applying that force is the pressure.
Thank you.
Mhm.